today we get to do, it's one of those days where you got to really, really focus because but if you do, you're going to get this. But you have to, if you don't follow along, you can't be lazy with this. You got to really be engaged and focused. So we're going to finish talking about transformations of functions. And just to review real quick, it's been a couple days, we had 3 numbers that we could plug in and take a basic parent graph and turn it into any kind of version of that graph that we want to. We can make it more complicated, right? So we said one of them was H. What we've talked about. What does H do? Okay, that's horizontal translation. And remember, that's the number that is being subtracted from X inside the function, right? Okay, what does K do? Vertical translation. That's the number that's being added outside of everything. And then the new number that we haven't really talked about yet, we're going to talk about today, is A, the vertical dilation factor. And that's the coefficient that's being multiplied by the function out in front. Okay? And it does some important things that we're going to look at today. So first of all, I'll tell you what, we'll come back to this. Well, no, let's not. Let's look at this page. So H and K just slide this thing horizontally and vertically to position the graph someplace in the XY plane. But they're isometric transformations. They're not changing the shape or the size, just the location. A does something different. A is a dilation, right? Now you guys are used to, in geometry, a different kind of dilation. The dilations you talked about last year, they either took the whole object and proportionally inflated it or deflated it, right? So it changed in all, he's not here. It changed horizontally and vertically proportionally, right? We got the same shape but just a bigger version, for example. That's not what we're doing. What we're doing with A is only a vertical dilation. The width is going to stay the same, but we're either going to stretch it vertically or compress it vertically without changing the width. Okay, so let's explore this just a little bit. Oh, reminder, here's our guinea pig, our parent graph, because it's so easy to graph. We're using an absolute value function, right? Just a V, the vertex starts off at the origin, right? And then it's just a right leg has a slope of 1, left leg has a slope of -1. Couldn't be easier, right? Easiest function to graph, that's why we pick it. Okay, what happens, do you suppose, if we multiply a function by a number bigger than 1? What do you think that's going to do? Let's explore. So here's our parent graph, right? Just like before, there's our V-shaped absolute value function. Now the red graph that we're going to create is going to be the parent function multiplied by A, but A is starting off with a value of 1. So it hasn't done anything, right? F of x is exactly the same as our parent function because we've only multiplied it by 1, which hasn't changed it. What if I multiply it by 2? What is that going to do? Okay, I've seen people, and you gotta be careful. It's not doing anything horizontally. Horizontally, it doesn't get changed. It doesn't get stretched or compressed. It's all going to be vertically, so that's going to vertically stretch it, right? Let's see what that looks like. If I stretch this thing, let me make one little quick change here. Okay, if I stretch this thing by a factor of 2, look what it does. It takes all those points and they just get stretched out vertically, don't they? So now, instead of going 1 to the right and up 1 like I normally would on my parent graph, I go 1 to the right and up 1 times 2. So I'm going up 2. Instead of going over 2 and up 2, I go over 2 and up 2 times 2. I go up by 4. Well, what if I made A equal to 3? What would that do? Stretch it even more. Yeah, I'm stretching it now by a factor of 3. And look what that does. Instead of going over 2 and up 2, I go over 2 and up 2 times 3. I go up 6. Okay, give me thumbs on that. Does that make sense? Okay, what would happen if I made A a number like 1/2? Okay, that's going to squish it. So everything's only going to be 1/2 as tall as it used to be, right? So if we drag, if I drag A down here to, that we're starting at 1, now watch what happens if I drag it down to 1/2. Oh, look what it did. It just squashed everything so it's only half as tall as it used to be. Okay? Give me 1 to 5 on that. Everybody see what's going on? Okay? Good. All right. So, if A is greater than 1, it stretches it by a factor of A. If A is less than 1, it compresses it by a factor of A. What do you think happens if A is negative? Yeah, it's going to, and really, it's pretty predictable because we're going to do the same kind of thing we did before, right? If I normally go over 2 and up 2, what if A is equal to -2? Well, then I'm going to go over 2 and up 2 times -2. Well, that's -4. What do you think it means to go up -4? I'm going down 4, right? Good, so if I let A equal -2, that's what happens, right? Everything gets stretched downward this time. So we could think of it as doing two things. It's going to reflect the graph and stretch it. Reflect it because it's negative, stretch it because the value is, it's a number bigger than 1. Everybody get that? Okay. All right, so we've got a pretty good foundation then in what A does. Let's practice this a little bit. So the game we're going to play now is just recognizing the values of the parameters and picking out what the parent function is. What kind of a graph are we dealing with? So first of all, can you guys all tell me, based on what we've been doing already for a few days, what's the value of H? -2? I think you're close, but I disagree. 2, right? 2. How come? Well, you tell me, which direction would this thing slide horizontally? It's going to go to the right, isn't it? Okay. So is that the positive or negative x direction? To the right. That's positive, right? On the x-axis, that's the positive direction. So because it's sliding, H tells you the horizontal translation. Well, H has to be a positive number if it's sliding in the positive direction, and it is. This is the tricky one. Remember, it's always going to be the opposite of whatever that, the way that the number is attached to x inside the function, either by subtraction or addition, we're going to do the opposite of what that operation seems to imply. We're subtracting, but we're subtracting a positive number. So H is +2. So we're going, and again, what's that telling us? That's telling us we're going right by 2. What's the value of K? 1. Good. So what's that tell us? Yeah, we're going up 1. What's the value of A? 3. What's that tell us? Yeah, so that's going to be a vertical stretch. So how do we, I guess maybe we say that like that. We're stretching it, right? Can you tell me what the parent function is? If I just got rid of all those parameters, those numbers, what kind of plain old graph would I be left with? Close. What would happen if I got rid of the 3 and the 2 and the 1? What am I left with? What kind of function? Absolute value. That's it, right? It's just an absolute value of x. Our vanilla parent function would have been an absolute value of x, and then we souped it up and made it more, made it more interesting by adding all these values of our parameters a, h, and k. But without those parameters, we're just left with a boring old absolute value function. Okay, give me 1 to 5. How are we doing? Okay, all right. Let's try another one. Okay, think about the value of h, everybody, real quick. What do you think? What's h going to be? Casey, what do you think h is? -1. Good. -1. It's the opposite of that operation. Good. So that means point which direction it's sliding horizontally? Yeah, going to the left by 1. What's k? 0. Yeah, how come? Because what's being added outside the function? Nothing. So we're not translating this thing vertically at all, right? Let's see, what about the value of a? Negative 1/3. So what's that tell you about what's happening to the function? Squished and flipped it. So it's been reflected. Okay, good. Can you guys tell me, now, we haven't talked about, what is the parent function, by the way? What do you think? It's not an absolute value of x this time. It's something different. If I just got rid of all the values of a, h, and k, what would be left? Say it again. But there's no, I don't see any absolute value bars there. It's not absolute value. What would we be left with? Okay, there is an exponent, right? The parent graph would just be y equals what? Has to have an x in it. I mean, x is our variable. X squared, that's it, right? This would just be, if I got rid of all those parameters and just made the most boring version of this kind of graph, it would just be an x squared graph. Everybody get that? Okay, now x squared, if I graph an x squared function, if I graph y equals x squared, what's it look like? It's just a parabola. So it's kind of a U-shaped graph instead of a V-shaped graph. It's a little bit harder to graph those, which is why we start off with an absolute value function. Where's the vertex of a parabola like this, of x squared? It's kind of the point of the U, the bottom of the U. What's the location of that for my parent graph? 0, 0. Okay. Can you guys tell me what the location of the vertex would be for f of x? Zero, zero? No, we've not really, because we've done something to it. Was it? Negative 1, 0, exactly. How come? Because we moved it over, right? We took this whole graph and we slid the whole graph left by 1, and vertically we didn't do anything, right? Okay, so if the vertex starts off at the coordinate 0, 0, it's always going to end up wherever h and k tell us to slide it, correct? Okay, so we always know that the vertex of a function that has a vertex always is going to be at coordinates hk. So when I pick out the values of h and k, I'm really just finding the location of the vertex for that function, which makes it really easy to graph, because that tells us the location of the function, and then we just need to know what shape is it going to be, right? Okay, you start to see how we're approaching this stuff? Can anybody tell me what the parent function is going to be here? Square root of x. Absolutely. The easiest version of this one would just be a square root of x function. What's the value of h, everybody? Negative 4. So, okay, that tells us we've translated a little bit. What's k? Negative 7. Okay. Now this function doesn't really have a vertex, but it has a starting point at the origin for our parent graph. So can you tell me, we're going to call it a vertex even though it's really not. Can you tell me what the new starting point would be for this function? Negative 4, negative 7. And in this case, the starting point, it's a little, we'll talk about this later in the year. The starting point looks like that for a square root graph. And so what we're going to do, that starting point of the graph is just going to get moved over 4 and down 7, left 4 and down 7, and we would just start it in a different place. What's the value of a? No, okay. Is it 0? Because it's the number that's being multiplied out front. Okay. So if a number that's being multiplied is invisible, it's not a 0, it's a 1, right? For example, if I gave you the line y equals x plus 3, that's in slope-intercept form, right? What's the slope? 1, because that's the coefficient of x, right? That's m. What's the y-intercept b? 3, okay? So you already know this stuff. So a is 1, good. Okay, I'm going to really challenge you. Here's some very weird ones. You don't even know what this function is. But can you guess what the parent graph, what is the parent function? Well, okay, that's actually an ln, stands for natural log. So the parent function Even though you have no idea what this thing looks like, it's just log x, natural log x. Okay? We don't know what it looks like, but if we did, and you know, maybe at the end of this year, for sure next year, you guys will know what that looks like. We still know what to do with it here. What's h? 0. Okay? So it hasn't been translated horizontally at all. What's k? 5. So whatever it looks like, we know that it's been translated vertically by 5. And what's a? Okay, so what have we done to it? What's that do to it? Yeah, so we don't know what it looks like yet, but if we did, we would know that it's going to get translated 5 vertically and compressed by a factor of 4. So all we need to know is, what does that parent graph look like? And we would know exactly how to graph that function. Okay? Even weirder, and this is super tricky. Super tricky. Can anybody tell me what the value of h is here? No? Braden, you got an idea? No? What do you think? It's 12. Yeah. How come? Because that's the number that's being subtracted directly from x is 12. Okay, what's k? Well, negative pi. Yeah. Okay, so that's a little weird. So we know, again, we don't know what this function is going to look like, but we know that it's been slid to the right by 12 and down by pi, right? What's a? It's 3. Yeah. Because that's the number that's being multiplied by this thing out front. Well, if I got rid of all those parameters, if I just erased them, I'd be left with the boring version of this function, the parent graph, and what would it be? 2 to the x. So it's an exponential function, 2 to the x. Okay? That's a pretty tricky one. Give me 1 to 5 though. How are we doing? That makes sense? At least why those are the numbers? Okay. So now let's practice graphing these things, right? And so we're going to use what's called the vertex form method, which makes it easy, right? So by finding the values of h and k, we know where to place the vertex, which gives us the location of our function. And we're going to be using absolute value functions to begin with, right? Okay, what do we do next? Well, we got to get the shape of this thing, and we get that. There's 2 ways we can do this, but we're going to limit ourselves for now. There is a method where we could just stretch the function from its vertex or compress it, but I think that's just a little bit confusing at first. We'll come back maybe later and look at why that works, but we're going to do something just to be consistent and something that works for any function. It's so versatile. We're just going to use t-tables, right? So our goal is going to be, we're going to find the location of the vertex, and then we're going to pick an input value of x that's very close to h, that's close to the vertex, and then we'll plug that into the function and find a second point. And think about what we need to know to graph an absolute value function. When you're doing the homework online, what's it ask you to do? Well, you're supposed to pick a point for the vertex. We know what that is, though the coordinates are hk. And then I need to pick one other point to form the shape of the v, right? Okay, well, we'll just pick a value in our t-table, some other value, and plug it in to find that other point. So let's try this. What about one like this function? What's the value? It's an absolute value function, obviously. What's the value of a? -1. Because that's the number that's out in front of the absolute value, right? That's being multiplied by the absolute value. What's the value of h? -2. Good. And what's the value of k? -5. Okay. So then what are the coordinates of the vertex? -2, -5. Okay, and we could even add that onto our t-table. When x is -2, y is -5. And remember, if we read a t-table horizontally, it's just an ordered pair, right? So we know that the vertex of our parabola is going to be at -2, -5, so it's right there, okay? Okay, what does the vertical dilation factor do here? Just flips it. Does it stretch it? No, it's just going to flip it. Good. It only reflects the function. So that just gives us a kind of a heads up. What should we expect to happen? Okay, now our goal is to pick another convenient value of x to plug into our function. Okay, we could pick 1. We could. We want to pick something, if we can, that's pretty close to the vertex. Well, the x value of the vertex is -2. Now, my recommendation is, let's just be consistent and let's always go to the right of the vertex. Okay? So to the right of -1, I could pick, or of -2, I could pick -1, or I could pick 0. 0 is, if 0 works, if 0 is close to the vertex, that's a pretty convenient value to pick, because substituting 0 is very easy to do, right? If I pick an x coordinate of 0, and I want to find the corresponding value of y, really all I have to do is just plug 0 into my function, right? So I'm just going to calculate g of 0. Well, what is that? My y value is going to be g of 0. If I plug 0 in for x, what do I get? Negative absolute value of what? I'm plugging 0 in for x. 2 minus 5. Well, what's that equal to? What's the absolute value of 2? 2. Now, if we pick a value to the right of the vertex, I'm always going to get a positive number inside the absolute value bars, and so we can really even almost just ignore them. Right? This just is equal to -2 minus 5, which is what? -7. How about that? So we get 0, -7 for our second point. 0, -7 is right there, and then all I have to do, that's it, that's all I need, right? Once I know that other point, then the absolute value graph, that's all I need, because I can reflect that point and I get the shape of my graph. Start at the vertex, then I need one other point to determine the shape. We got it. Online, all you'd have to do is start with the red point and then add the blue point, and it graphs the function for you. Okay, give me thumbs. How we doing? Does that make sense? Let's try another one. Okay, this one's a little tricky. What's the value of a? 2 over 5. What's the value of h? 0. Nothing is being subtracted. Oops. Nothing is being subtracted from x inside the function. What's k, everybody? 0. So what's the origin? Or sorry, what's, I gave it away. What's the vertex? The origin, yeah. Okay, what does the vertical dilation factor do here? It's going to squish it, because 2/5 is less than 1, right? So it's going to squish it or compress it. Okay, so we know that the vertex has coordinates 0, 0. So there it is, right there. What would be a good value of x to pick for our second? I could pick 1, sure. I could plug 1 in. If I plug 1 in for x, I'm going to get 2/5 times the absolute value of 1. What's that? Ooh, that's not very convenient. Can you think of maybe a better value of x that might be more convenient, that would be easier to graph? 5 would be a good one. How come? And it's going to, okay, it's a 5 is a multiple of 5, so it'll cross the denominator out. It'll clear the fraction, won't it? Right? Yeah, 5 would be a great choice. So let's pick 5. Okay, we'll pick 5, and then that gives us the ordered pair 5, 2. So over 5 and up 2, hey, we got it, right? That's all we need is a vertex and one other point, and we got it. Okay? Everybody see that? Let's try again. Let's just practice this a little bit. Show me with your fingers, everybody, what's A? Okay, good. Like what I'm seeing. What's H? Okay. You got to be a little creative here, but what's K? Okay, I like it. Negative, that's kind of hard to do. -6. Okay. And so the vertex is at 5, negative 6. Okay, so we can just add that. Oops. Our vertex is at 5, negative 6. So we'll take this vertex, which normally would be at the origin, and it's going to be over 5 and down 6. And I want you to think about this for a second. We want another good choice for x. I mean, I could. But we'd probably, if possible, maybe like to pick one that's to the right of 5. So how about 6? Yeah, why not just pick 6? Right? If I choose an x value of 6, which means I'm just plugging 6 into my function, what's the y value going to be? I bet you, just see if you can do that in your head. Negative 3, I agree, right? How come? Well, look what we're going to get. If I plug in, do down here, f of 6 just means 3 times the absolute value of 6 minus 5 minus 6. Well, what's the absolute value of 6 minus 5? 1. So that's just giving me 3 times 1 minus 6. What is it? 3 minus 6? Yeah, it's just negative 3. So over 6 and down 3. Remember, our vertex was at 5, negative 6, and that's all we need, right? Because I know if I get a point on the right of my axis of symmetry, I get a corresponding point on the left. And now I can just graph this thing. And it looks like it should. It got stretched vertically, didn't it? Okay, now, that combines all the stuff. Give me 1 to 5 on that. How are we doing? Be honest, I want to get good feedback here. Okay. Okay. All right, we're getting there. 2 more examples and we're done. I'm going to turn you loose and let you work on this. Okay. Show me with your fingers what's A. Okay, good. I'm seeing negative 2s. I like it. What's H? That's a tough one. Yeah, hard to do. Negative 6. Oh, I like that. That was good. Okay. Negative 6. That was. See, do that again. Yeah, that's pretty good. Okay. Negative 6. What's K? Negative 3, right? So we know then the vertex is at negative 6, negative 3. So negative 6, negative 3, there's my vertex. Okay, what's a good value of x for us to input here? Yeah, I just want to go to the right of negative 6, so I want an x value that's a little bit greater than negative 6, so what about like negative 5? Negative 5 is fine. If I plug negative 5 into my function, what am I going to get back for y? Think about it for a second. What's the absolute value of negative 5 plus 6? 1 times negative 2. Negative 2 minus 3. Well, negative 2 minus 3 is negative 5. Remember, subtracting is the same as adding a negative. So that would be the same as saying negative 2 plus negative 3, which is negative 5. Okay, so negative 5 puts us, yeah, negative 5 puts us right there. And so we got it, right? There's our V. Okay, last one. Hardest one I could think of. Hardest one I could think of. You can do this one, you can do any of them. What's A? Negative 4/3. I agree. What's H, everybody? Negative 1. Show me with your fingers, what's K? All right, 2. Outstanding. So my vertex is at negative 1, positive 2. Okay. So negative 1, positive 2 is right there is my vertex. What would be a wise choice, and this is a little tricky, what would be a wise choice for X here? If I plug in 0, I mean 0 is going to work, but it's just not convenient. If I plug in 0, I get negative 4/3 times 1, which is a fraction. 2 would be good. I like 2. Okay, 2 is great because look what happens if I pick 2. If I pick 2, then I get my y value is going to be negative 4/3 times, well, if that's a 2, what do I get from my absolute values? 2 plus 1 is 3. Absolute value of 3 is 3. That's perfect. What's negative 4/3 times 3? Negative 4, because the 3's cancel. Negative 4 plus 2 is negative 2. So over 2, down 2, we got it. Okay. Hey, Brianna. Yes, I will. Okay, perfect. Okay, bye. You know about this? You going home? Yeah. Yeah. Okay, so then we got, let's see, if we were graphing this without technology, that's 3 to the right, so we would just reflect it over and get one on the left. That's 3 to the left. And then we just graph our function, right, our V. And we're done. Make sense? Okay, get to work.